Welcome to Rad2, another daily reader for Reddit. Like and subscribe for daily Reddit videos. If we return to the moon, is there a telescope on Earth today strong enough to watch astronauts walking around on the surface? No, I don't think any telescope could come close. For instance, Hubble has an angular resolution of about 1/10 of an arcsecond. It is approximately 384,000 kilometers from the moon. 1/10 arcsecond is 1/36,000th of a degree, and a circle is 360 degrees. 1/10 arcsecond on a circle with radius 384,000 kilometers is 2 * 384,000 * pi 360 36,000th c equals 0.18617, so the resolution of Hubble would be 186 meters. Much too large to make out a single human. To achieve the sub-1 meter resolution needed to discern a person on the moon, a telescope would need a resolution over 100 times better, which does not exist. So the resolution of Hubble would be 186 meters per pixel. In case someone thinks that's the width covered by the image. Great caveat. Thank you. So, 100 times more powerful than Hubble? Wasn't Hubble a gift to NASA from the NRO, or at least based on a design that was technically, for its time, a previous gen keyhole satellite? I remember from somewhere that Hubble is almost 1-to-1 a KH-11 keyhole satellite that is pointed at the stars rather than Earth. In addition to this, aren't the replacements for Hubble supposed to be built around handy-down keyhole sats given to NASA by the NRO? It's impossible to get information on the current gen of keyhole sats, or even that they exist other than rumors. But 100 times more powerful than 1970s technology doesn't seem that extreme. From seeing a few of the imaging sensors developed for current, next-gen NRO assets, and with all their optical lens breakthroughs over the past decade and a half that get announced then acquired for exclusive use for US defense, it doesn't seem outside the realm of possibility that the tech exists but just isn't available for use outside the intelligence community. Caret. Edit. Added link. It's impossible to get information on the current gen of keyhole sats, or even that they exist other than rumors. But 100 times more powerful than 1970s technology doesn't seem that extreme. When Yerich is talking about 100 times more powerful, that means 100 times bigger. 100 times larger is hard enough to achieve on the ground. en.wikipedia.org. As you can see from the list, we're nowhere close to that yet. Launching something as large as the big ground telescopes into space is well beyond current capabilities. You'd be better off putting a better optical telescope in the orbit of the moon. By 100 times bigger, do you mean 100 times the area, or 100 times the diameter, or 100 times the focal length? I believe they mean diameter. There's a fundamental max resolution that is a function of the diameter of your light collecting area. This is called Dawes limit. I'm an astrophysicist, and I believe the answer is yes, maybe. First we need to calculate the angular size of an approximately 2-meter astronaut on the moon. We can do this easily on Wolfram Alpha. We find that the astronaut is about 1.04 milliseconds. As other users have pointed out, no single telescope is large enough to have this kind of angular resolution. Hubble is about 100x too small. Typically, to resolve an object, you need the resolution to be at most half of the object's size. So you'd need a resolution of less than 0.5 milliseconds. But you don't need a telescope 100x bigger than Hubble to have 100x Hubble's resolution. An interferometer is an array of telescopes that have the light-gathering power of their total mirror areas, but the effective angular resolution is determined by their most separated elements. The most powerful optical interferometer in the world is the Chara array, located on Mt. Wilson. It's a series of 6 1-meter telescopes that are about 330 meters apart at longest separation. This means it has a resolution of a 330-meter telescope. Chara has an angular resolution of 0.2 milliseconds, which should be plenty to detect our astronauts. Update. 7 hours later, someone asked a question that led me to think of an obvious concern. Why the astronaut be bright enough to be visible by a small telescope array like Chara? The moon reflects approximately 12% of the light that hits it. Let's assume an astronaut is wearing a classic white spacesuit. That reflects approximately 80% of the light that hits it. Let's say then, that for equal angular sizes, Astronauts are 6x brighter than the Moon's surface. The Moon has a surface brightness of approximately 4 arcsecond carat. 2. If an astronaut has an angular size of approximately 1 mass, then let's say they have a solid angle of approximately 1 mass carat. 2. Then they are 6 by 1 mass carat. 2. 1 arcsecond carat. 2 equals 6 times fainter than a square arcsecond of the Moon, which means their apparent magnitude is approximately 13 plus 4 equals 17. What sort of exposure time is needed to see a 17th mag object? Well, on the Kitt Peak National Observatory 0.9 meters telescope, it looks like to get a signal-to-noise ratio of 10, we need an exposure time of 0.7 seconds. But Chara has 6 telescopes that are a bit bigger at 1.0 meters. So let's call this 0.76 asterisk 1.0 0.9 squared equals approximately 0.1 seconds. But I'm going to assume that optical interferometry is more lossy than a simple imager, like in the KPNO example. So let's just arbitrarily bump this up to 0.2 seconds. I'm not certain what sort of exposure time is necessary for a ground-based telescope like Chara to work well but their user's manual has an example where they use an exposure time of 8 milliseconds now. Is this fast exposure time needed in order to be smaller than the time scale of atmospheric variations? If so, then it's hopeless for our astronaut project. But if it's instead the case that Chara had a rapid exposure time in this example because their target is very bright, then we may still be in business. Chara might be observing bright targets because they are big, because they are close, which is also why they are bright, rather than because they can only see bright things. In this case, Chara could afford to take slightly longer exposure times of approximately 0.2 seconds for our astronaut, even if that's a bit slower than the atmospheric coherence timescale, which is usually taken to be 0.01 to 0.1 seconds or so, depending on lots of stuff. So, because I don't know CHARA's upper limit for exposure time, if there is one, I must offer an unsatisfying conclusion of maybe, edit, had the wrong link for Chara initially. Fixed now. Thanks for watching Rad2. Like and subscribe for daily Reddit videos. If you like these videos, check out the original Rad channel.